So hello and good day. So we are going to run through the basic implementation of neural networks. This is just a very brief sketch of it. What neural network essentially is, just to build out the mathematical expression of it and build the data structures for the mathematical expressions. So they can just see what at the core is neural network. So neural networks are basically massive mathematical expressions, and you're going to need data structures that will be able to maintain these expressions. So we start out by building the value class that will contain the data structures and also the mathematical expressions. So the value class. So it has the init function. So data. So this collects the single scalar value and wraps around it and keeps track of it. So for example now, we can see like A is equals to value 2.0. So A is this. Why we are seeing this instruction is that there's no repo function already. So you get a very ugly expression. In order to remove this and to keep it in a way that we can easily read, so we don't get this something that is cryptic, we are going to add a repo function. So this is the repo function. So it returns value data is equals to self data. So now we're going to have that ugly data expression of our object, value object. So if we have another create another value, say b is equals to value and 3.0, you see that if you try to add it now, it's not going to be able to work out. So you have a plus b. So you have this, and then we have a plus b. It's going to flag an error, the type error, that those operated operands of types of value and value. The reason why is this happening is because Python does not know how to add two objects. So we have to tell Python how to add two objects. So we are going to use special inclusive methods, double inclusive methods in Python to define these operations. So for example, this operation of addition, we're going to create these special inclusive methods. So which is this. So we are going to use the add function. And so we have this, the value self.data plus order.data, and it's going to return out. So what this is, it has this self is the first object, then the order is the second object. So it adds the two of them and then brings it out. So if you use this plus operator, what you are doing is that Python is calling internally this. So it performs, instead of doing see what Python does internally. So it calls this and then uses the add operator and then adds this b to it. So if you run this now, it will give you the value of -1 because 2 minus 3 is 1. So but since we've already defined this inside here, we can simply also call a plus b, and it's going to give us -1. So in similar vein, that is also what happens when we do the multiplication. So if we have our multiplication function, so def multiplication, so we have the self, we have the order, and then out is equals to value self data times order dot data. The returns equals to this. So that's what happens. So if you also run the same operation, a dot mol of b, which is actually 2 times minus 3, which is minus 6. They give us minus 6 as our answer. So now we can also add one another variable now. So let us add c as a variable here. C is equals to let's say 10 value 10.0, and then we want to perform the operation of a times b plus c. A times b plus c. A times b is already 2 minus times minus 3, which is minus 6, plus b. 10 minus 6 is 4, so it's supposed to give us 4. Now so in this operation now we are going to have like a connecting tissue of this operation. What it means is that we need to keep this expression graph that be able to now keep um, num- um, numbers about what values produces the other values. So for example, if you have like 2 and minus 3, if you add them, it's going to give you minus 1. We need to have, so if you give out minus 1, we need to know what are the values that produced the minus 1, which is in this case is 2 and minus 3. So we're going to introduce a new variable in our class function. So the variable is, let's call it children. And it's going to be an empty tuple, right? And then there's also the variable should be named previous. So in this case, still it's going to be a set of the children. So like I already said that by default the children is going to be an empty tuple, and then once it comes into the function, into this the initialize function, we named it previous, and it's going to be of the set of the children. It's for the efficiency of it. So if you create a value through either so if you just create the variable from the construction, so for example, if you just create value of 2 and 3, it's going to be empty set. But if you're going to create value from addition and multiplication, it's going to be fed. You're going to feed in the children. You're going to feed in the children of this into the value of the value into the function. So in this case now we're going to put in the children here for add and also for multiplication. So what are the children for? For add, the tuple is going to be the tuple of self and then order. The same thing also happens here. No, it's actually here. There's supposed to be self and then order. And also here, we're going to have the tuple of self and then order. These are the children, which is this self and then order. We're feeding in the tuple of the children into this children variable here. So we can be able to have a trace of the children that produced the value that you're working on. So now we now have a previous function. So for example, if you have okay, we run this, and let us say that this variable, this value is supposed to assign d now. I want to see our d variable now. So normally it's 4.0. Now, if you want to see d.previews to preview, you are going to see now these are -6 and 10 because a times b gave us -6. That's 2 times -3, and then c is already 10. Is this 2 that we added together to give us our 4? So we're keeping track of the children of the value of d. Now we know the children of the value, but we do not know the operation that created these children. So we're going to assign a new value called operations in our init function to be able to keep track. At the beginning, this is going to be equals to, it's an empty string, and then we're going to create this here, the variable operation called op, right? So inside here now, the addition, we're going to put in the sign of plus, and then for the multiplication, we're going to put in the sign of multiplication here. It's supposed to be inside here. The plus multiplication, the plus sign, and then also the multiplication. Here's the multiplication. I'm wrong here. Okay. I think it should be here. I think it should be here. So in this case now, we are going to put in the sign of for addition in here, and then we also put in the sign for the multiplication here. So in this case, it works out now. So if we have our d now, since it's gotten from multiplication, from addition rather, so we have d dot the operation. It's going to give us the addition sign, right? So we now have the full mathematical expression. So we are going to build out this data structure. We've already built out the data structure. So now the expressions are trying to get a little bit large. So we are going to find a nicer way to visualize the expression. So we're going to bring in a body of code that does that visualization. It's going to be like a large body of code. Don't bother that that it's a little bit complex. So but with time, we're able to explain how the code works out as in subsequent time in the class. So this is the code that does the visualization. You can read about the graphics online. Check about its implementation, the functions and the modules that are in it. So see in here we have the trace shoes and also the draw roots. So this draw root function is called on the root node, and to be able to visualize the node, right? And then the trace function, it enumerates all the nodes and edges in the graph in the graph. So now we can visualize. So let us run this now, and then so let us see if we can visualize our d. Our d is already d here is supposed to a times b plus c. So but we can walk around here now. Let us see if we can. We usually have level here now. Okay, so let us just visualize draw dot. and call D in it. So you see, we can see our delta is 2, 3, 2, and minus 3. To add it to multiply it to give us minus 6. And then 10 minus 6 in the addition, it gives us 4. Right? So, but now we want to see if we can walk around here. So let us make it a little bit deeper. A little bit of layer deeper. So in this case now we have A times B. We have E is A times B. So E level. Did we even create levels? Okay, we're supposed to let us see if we can add levels here. So that's another area we're going to work on now. So let us still keep this thing. A plus B plus C. So label in this function, in this graph now, you see that we don't really know which variables gave us these things. So we need to put in labels to be able to understand what variables are the ones that gave us this. So in this case, we're going to have like label is supposed to, it's going to be empty, and then you have self.label is opposed to label. So we are going to have a modification of here. So in this case, we're going to have a new sign here. So end.label, end.data, end.label, end.data. So now we can see the label here appearing. There's a little bit of error here. Okay. So we're going to have the end of label. So we already added a label and also created the variable in our class. So we're going to put in the label here. So here now we're going to put label. Label is supposed to A. So label is supposed to B. Label is supposed to C. So we have D here. So we're going to say D.label is supposed to have T. So that's that. Run this and then here. So we see the label has appeared. So we have our A, our B, then C, E. So you need to put in the E label. A plus B. Oh, so we're going to create like a new. So this A plus B has to be. So we have E is equal to A plus B. E is equal to A times B. A times B. E dot label is equal to E. So we remove this and add it as E. I think it works fine now. So we have our A, B, E, C, and then D. So let us okay, making it a little bit deeper than it was. Let us also add another value here now. So we already have D. So let us call it F. It's supposed to now value minus 2.0 label is opposed to F. So L, that's the loss function. The outer value is going to be T times F. Then L dot label is opposed to L. So if we print our L now, it is going to give us the value of minus 8. So let us also run it here to see the effect it has here. Okay. So So L, you're going to put in L here. So A, B, C, E, then D, F, and then our L. So let us make a recap of what you have been doing since. So we built a mathematical expression using the plus and the multiplicative sign, so forth. So there are scalar values which we are along the way. So we now do a forward pass, and then so we built out actually. So it's actually a forward pass that we did. It's not that we are going to do. So we do a forward pass and built out a mathematical expression. A times B to give us E, E plus C to give us D, D times F to give us L. That is the forward pass. We have built out the multiple expression, which are the multiple inputs consisting of A, B, C, D, and F going into L. So we made a mathematical expression that produces the single output L. And then we visualized the forward pass. Next, now we're going to do the backward propagation. This is where the neural network comes in, and then the crux of neural network now comes in. So we now start from L, from the end, and then we reverse and then calculate the gradients along these intermediate values. So for every single value, we compute the derivative of that node with respect to L. So L is the loss function. So we're going to calculate the derivative of each node with respect to L. So we talk about the d over d with respect to L. So we're going to calculate the L over the D, the L over the F. So in this case, goes with the L over the C, the L over the E. So the L over the A, the L over the B. But these are the weights C, E, D, F. So these are the ones we are going to work on. We can also do this for A and B, but these are like the data and they are fixed. So we are going to more like leave them and simply work on the weights. So we see how much of the influence we make in the weights we affect the. So that's actually what derivatives is. What change in weights are we going to make to affect the loss function. So we're going to be twisting our weights to be able to affect our loss, or like fine tuning our weights. So every change in our weights affects L. So the change, so the change in our weight over the change in L, that is derivative, that is calculus. So it's change of loss over change of weights. How the weights are impacting the loss function, right? So the weights will be iterated on using the gradient information. And then so we're going to create a variable with a value class that maintains the derivative of L with respect to any value. So we are going to call that variable grad. So here we have self.grad is equals to 0. Now it's going to be 0, the float number of 0, because it means that there is no yet effect on that. So the gradients will still be 0. So initialization will assume that any value that does not affect and does not impact the output. That's the loss function. So we want to visualize this grad to see it. So we come to our place for visualization. We're going to add the grad here. So the grad is the percentage of 44. And we're going to add it here. N.grad. So it's going to show both the data and the grad. So I think it will work here. So we already have our grad, and you have the variable that contains the grad, and then you've already added it here in our node. So we're able to express the grad. So we now run it here now. So we now see our grad. So the grad is initialization is actually zero. Zero initialization, right? So we're going to have a function, a numerical representation of gradients to see how much of the nudge we make in the gradient will affect, um, how much nudge we make in the width will affect the loss. So we're going to have a function that has these variables here. So this is our L. So we copy this. So for example, we call it like this function, and then we're going to paste this here. So something like this. So this is our loss function. So we have another of it here. So what we are doing here is so that it will not affect the global variables. So this will be the local variables you are going to work on. So after this, so this is going to be like our L1 is equal to L. This is going to be like our L2 is equal to L. So we're going to print in the change of this. We're going to print in the change of L2 minus L1 over the change. So we have a H here also that contains the slight deflection, like a little change in our in our weights. So this is what this thing does here. So now I think it's going to give us 0. It's going to print 0. So if you call this function now, okay, let's put it here. So I think what happens here is going to be the data, because this is a value. So we need to access the information. Let's see. Okay, so you see, it's 0 now. It's giving us 0 because there is no change in the gradient. So if we, I don't know which one are we going to make use of now. So let us do change in D. So now you know that in calculus now, if you want to calculate the gradient for D now, the gradient of this with respect to this, so dl over the D, since it's a multiplication, it's supposed to be F. So if you differentiate L with respect to D, it's going to give us F. So like if you come here now, and we have in our calculus now, so we have like, so we have L now is equals to D times F. So we want to calculate the change in our L over the change in D. What is it going to give us? So it's supposed to give us F. But if you want to see it in the expression, the one used by the Newton, by Newton. So for example, you have F x plus h minus F x divided by h. So it's going to be the change in the first function. So you have D plus h times F minus D times F. Then you divide it by h. If you expand this, it's going to be D times F plus h times F minus d times f over h. So this d and f cancels out to give us h times f divided by h, which eventually gives us f. So it's actually f. And the value for f here is minus 2. So if we change d slightly, we are going to get the value of minus 2 as the change of L with respect to changing d. So let us change d a little bit here. So it happens here in this second part. So we have d dot theta is going to be d dot theta plus h. So there's a slight change of our d using this value of 0.01. Let us see the value is going to give us. You see, it is giving us minus 2. So it means analytically it's correct. And minus 2 is actually the value of f here. Minus 2. So symmetrically also, if you do the L, if you also do, if you come here and also do the L over the f, is going to give us d. So our d is what here? Our d is 4. So if you change, instead of this now, we are going to change our f. Where is f? F is here. F dot theta. I'm going to do it equals to h. It's going to give us 4. And 4 is the value for d. It's a 3.99. If you add, maybe let me just increase it a little bit. See, it's giving us 4. So it means that it's numerically verified. It's correct. Verified. It's numerically verified. So now we are going to come into the crux of backpropagation. What essentially is the backpropagation? And this is the most important part of what we are learning in neural nets. Because if you be able to understand the gradient of this node, so we are finished doing this f and d, this gradient of this node that is plus, you'll be able to understand all backpropagation and also the training of neural network. So here now, see what we are going to do now. We have the L over the C. We need to derive the L over the C. So we are going to derive the L over the C. But we don't have that information now. What we know the L over the D, which is what we just calculated. How sensitive L is whenever we change D. But what we're trying to find is how sensitive is L whenever we change C. So we know the L over the D. But we also know how sensitive D is with any change in C. So we know the D over the C. But that is not what we are looking for, because this is the local derivative. We're looking about the global derivative. What we are looking for is not the D over the C. We're looking for the L over the C. But the beautiful thing about it is that if you know the impact of C on D, and also know the impact of D on L, then we can know the impact of C. The impact C has over L. So now let us write it out here now. So we have the L over the C. Or maybe we just remove this so to have a clearer version of what we're doing. So this is what we are looking for. So but we know that D is equals to C plus E. So if you differentiate the D over the C, it's going to give us 1. So if you have the D over the C, the value is going to give us, because if you know any plus operation in derivative, you can differentiate the D over the C. it's not multiplication, it's addition. So with respect to c, it's going to give us 1. So if you want to write it out, you can still write it out here to see whether it's true or not. So we have fx plus h minus fx. So you're dividing everything by h. So we have slight change in our d. So which is c plus h plus e minus c plus e. Everything in caps, put in a bracket. Then we now divide it by h. So if you expand the bracket, it's going to be c plus h plus e minus c minus e divided by h, which is, so the c cancels out, e cancels out, it gives us h divided by h, which is basically is actually 1. So that is the local derivative. So we are going to make use. So the d over the c is 1. Even by symmetry also. So this is 1.0. By symmetry also, d over de is equals to 1.0. But like I said, it's local derivative. What you're looking for is dl over the c. So how are we going to put in the influence of c with d and also the influence of d with l? Like we say that if you know this influence of c with d and know the influence of d with l, you can calculate the influence of c with l, the influence of c on l. The solution to that is the chain rule in calculus. So if you remember your calculus here, so this is the chain rule. So we have the z over x. So we want to see the influence of x on z, but we know the influence of y on z. I know the influence of x on y. So the influence of x on z is the multiplication of influence of y on z and influence of x on y. So you can see where is a beautiful explanation of this. So George Simmons now said that if a car travels twice as fast as a bicycle, and a bicycle travels 4 times as fast as a walking man, then the car travels 2 times 4, 8 times as fast as the walking man. So how far the car travels as fast as a walking man, we don't know, but we know that the car travels twice as fast as a bicycle. And then the bicycle travels 4 times as fast as a walking man. So we chain this rate with this rate to get us the influence of how fast the car travels with respect to the walking man. That's the multiplication of that. So that's what we just do now. So we multiply the d over the c and the l over the d. So in this case now, our dl over the c is going to be the d over the c times dl over the d, dl over the d. So we already know our grads, E dot grad, and then our C dot grad. Our E dot grad is our E dot grad, like we calculated it, is 1.0, and then our C dot grad is equals to 1.0. I don't know whether we already added these ones. Okay, we've not yet added. So since we already, so we are going to add our grad here. So we know we already calculated the grad for this one, our L. If you remember when we calculated the gradients for L, there were no changes in this place now. So for example here now, so there's actually no change in any of them. So it's going to give us 0. So but if you change L, so what I want to do now is to calculate it from this function and then to populate it here. It has not yet been populated. So we need to get the gradient of L with respect to L. You need to get the L over the F, the L over the D, so that I can be able to get the L over the C. So the L over the L is change, so change of L. So we are going to calculate the L over the L. There is no change in L there's over change in, so we have the L over the L. So if there's a slight change in L, there's also the slight change also in L. So that slight change over the other slight change is going to give us 1. So it is this L2, follow along with what I'm doing. So we have L2 plus data. So we are going to increase it slightly. The slight change in L, so it's going to be L2 plus the change minus L1, which is the same thing as L2. The former the L2 cancels out, so it leaves us that change over that change, which is H. So it's going to be something like this. So if we remove this now, and we have the same function here now, so if we change our L plus H minus L, and we divide it by H, so that's the function, is slight change in that function. It's going to be, if you expand the bracket, L plus H minus L divided by H. L cancels out to give us H divided by H to give us 1. So the derivative of L with respect to L is actually 1, which is what we just did here. We just shifted it by 1. So we run it. L to the data. Oh, it's actually L2, so it's not like L to the data. It's going to give us 1, 0.99999. If you increase it again, I don't know if you increase it, it's going to be 1. See, it's going to give us 1.0. So we are going to populate our grad, L dot grad to be 1.0. And if we run this, we're going to see it here. Is 1.0. So it remains F and D. Remember what we did when we did for F and D. I think I've already considered that if you differentiate D with respect to L, so the L over the D is going to give us F, and if you differentiate, you have the L over the F, it's going to give us D. So we're going to assign our gradient. So it's going to be F dot grad is equals to 4.0, and then D dot grad is going to give us minus 2.0. So we have already assigned that. So here we are going to, what then is the gradient for this one now? For this our C. So it's going to be the D over the C times the L over the D. The D over the C times the L over the D. The D over the C times the L over the D. So, but we know the local gradient, the D over the C, which we did here. Which is actually what we did here. local gradient is 1. So the local gradient here, the d over the c is 1. The local gradient for this is 1. But the global gradient for it, which is the L over the d, is actually 4. The L over the d. No, so the value of d is 4 and the value of f is -2. So the global gradient, so the L over the d is actually -2. It's not 4. -2 is the gradient for this, which is f. The value of f is -2. So we are going to route f into these places. So it's going to be local gradient times the L over the d. The local gradient is 1 and the global gradient is the L over the d, which is f. So 1 times f is f, and our f is -2. So the gradient for c is -2, and then gradient for e is also -2. So we are doing a multiplication. What we are doing here is this times this. So this is equals to, so the L over the c is equals to, the d over the c is 1.0. We are multiplying it by the L over the d, which is the gradient of d, which is -2. Which is actually the value of f. This is the f here. So we are routing this gradient here, this is -2, into here and here. So internally, what the plus node does is that it literally routes the gradients, because the plus nodes are local derivatives and the differentiation of plus nodes are 1. So we multiply 1 times the global derivative, which is -2 in this case. And so the derivative gets routed to both c and d and e. So our e dot grad is going to be, now it's going to be 1, this is local derivative, times the global derivative, which is -2.0. And then our c dot grad is local derivative times minus times global derivative, which is actually, you just remove the 1, so it's 2.0, -2.0 minus 2.0. So it's the chain rule we just did here, the local times global, so that you can get the effect of the change of c with respect to L. How does the change in c affect our L? So if you do this now, we are going to put it in our graph now. So now our c and e is the gradient of this, which is -2. So we routed this into here and here because it's the plus sign. Remember the plus sign, the local derivative is 1 times the global derivative, which is -2. So we have -2 and -2 here. So this is the application of that chain rule. So imagine like it is flowing backwards from the graph. So what we just did now, that our back propagation, is that this gradient is flowing backwards depending on the effect it's having to each of the weights, right? So it's distributed the gradients or derivatives to the children of it. So if you want to check it out now to see our value, to see whether this E and C is going to give -2, let us place a little bit of change in E and also a little bit of change in C in our graph here. In this our to show that it's actually equals to -2, which is F. So we start with C. I think I should remove this. And then this. Remove this. So it just give us 0. So you change C a little bit. C dot data is supposed to plus equals to H. It's supposed to give us minus 2.0. So minus 1.999 approximately equals to minus 2.0. Minus 2.0. So it's correct. So let us do that for E also. E dot data is supposed to plus equals to H. It's supposed to also give us the same thing, minus 2.0. Exactly. It's minus 2.0. So these are the derivatives of the internal nodes. So this is just like a brief explanation of how we created our class for neural network. We built a data structure for the mathematical expression of the neural network. We did the forward pass of our neural network, which are the expressions of the mathematical expressions, till we get to the loss function. And then we did the back propagation, which is the gradient of the loss function affecting other gradients for each of the weights or the children of the nodes down to here now. And remember what we said, that we are going to leave this here because this is the data is fixed. So we are just concerned with the weights and how the gradient of the loss function affects them. These are the derivatives of the internal nodes for this. So we're going to stop here, and then in the subsequent class we're going to delve deeper into neural network in the basic expression of the neural network. So if you have any suggestions, you can also add in the code into the comment section. And so we'll see you in another time again. Thank you very much.